Hello and welcome to lesson 6D. I can use the geometric mean to find the lengths of the sides of a right triangle. Now, before we begin, I want us first to learn about a new term, and that is geometric mean. And basically, the geometric mean is a way of calculating a different kind of mean. You've heard of an arithmetic mean before, but this has to do mostly with geometry. And the way we set it up is we do a over x equals x over b, where x is your geometric mean of a and b. So for example, if I want to find the geometric mean of 4 and 18, I would do 4 over x equals x over 18. And then just like we were doing before, I'm going to cross multiply. So I get x squared equals 4 times 18, and 4 times 18 is 72. I'm going to take the square root of both sides. Well, 72 is the same thing as 36 times 2, so this simplifies to 6 square root 2, and that would be your geometric mean. So if I want to find the geometric mean of 6 and 15, we're going to set it, I want you guys to set it up real quick. All right, so now let's do it. We have 6 over x equals x over 15. We're going to cross multiply, so I get x squared equals 6 times 15. So I get x squared equals 90. Well, 90 is the same thing as 9 times 10, where 9 is 3 and 10 does not simplify. So you get 3 root 10. That is your geometric mean. So we actually can use a geometric mean to help us solve a variety of kind of problems dealing with right triangles. And there's a very cool theorem out there called the altitude of a right triangle theorem that states that if I have a right triangle, ABC, and I draw in an altitude such that B is the vertex of this altitude and we're drawing down to D, meaning it's the height of the triangle and I'm using AC as the base, okay, a little bit different than how we usually look at a right triangle, then this actually splits our right triangle into 3, you got the big triangle and the 2 smaller triangles, 3 similar right triangles, where they're all in proportion to each other. They're all similar. So for example, the shortest side on this triangle is AB. It would be in proportion to AD, which would be in proportion to BD. And my long leg, BC, would be in proportion to the long leg on my tiny triangle, which is BD, which would be in proportion to my long leg on the middle triangle, which is DC. And all of their hypotenuse would be in proportion. So the hypotenuse of the large triangle AC would be in proportion to AB, which would be in proportion to BC. The dots I'm using are not a standard notation. It's just a way for me to mark that they correspond somehow. So please don't think that that's a universally accepted thing in geometry. I just need some visual so y'all can see, no, they're not congruent, but they are in proportion to each other. So the first big theorem here basically states that the altitude of my large right triangle is actually the geometric mean of the 2 pieces of the large hypotenuse. And the reason for that, well, right here, this is my altitude. It's the long side on my tiny triangle, the short side on my medium triangle. And if you look, you can see it, as along the diagonal here, right? In the place of the geometric mean, right? Long leg of BCD, or short leg of BCD, long leg of ABD. And then the 2 pieces of the hypotenuse, this piece here and this piece here, AD and DC, that's the short leg and the long leg of the 2 triangles respectively. And they're across this diagonal. So if you break that down into segments, it's that your altitude is on one diagonal, right? This is the altitude. And the 2 pieces of your hypotenuse, AD and DC, are on the other diagonal, which we have written out for you right here. So guys, put a big star by this. This is a big idea, okay? And we'll be using it a lot. So let's look at an example of how we can actually use this. So here we can see that x is in fact an altitude, and that the 2 pieces are 2 and 8. So x must be the geometric mean of those 2 pieces. So I'm going to set up my proportion where I put x along one diagonal and the 2 pieces of the hypotenuse along the other, because that's how we find a geometric mean. and then we cross multiply. I get x squared equals 2 times 8, which is 16. So x must be 4. And that's all you got to do. So it's a quick and easy way to find pieces of a triangle where you don't have everything. There's another corollary to the right triangle theorem, and it states that basically that the length of the leg of a triangle is the geometric mean of the whole hypotenuse and the piece of the hypotenuse adjacent to the leg. So what does that mean? So now we're looking at legs of the triangle. And my legs of the triangle, let's just look at one at a time. If I'm looking right here at this leg of the hypotenuse, the short leg, that would mean that my short leg, or when I break it down, hypotenuse of the tiny triangle, right? It is the geometric mean of the whole hypotenuse, which in this case we're calling hypotenuse 1, and the piece of the hypotenuse adjacent to the leg, which is this AD right here, or this short piece here, 3. And the reason for that is that they are the corresponding pieces of these triangles, right? Similarly, if I look at the long leg here, this long 1, it's the geometric mean of the whole hypotenuse, again AC, and the piece of the hypotenuse adjacent to that leg, which in this case is DC. So let's do an example or two to show how this works. So here, when I look at this here, I'm going to ignore y for a minute because x is a leg. And so that leg must be the geometric mean of the whole hypotenuse and the piece of the hypotenuse adjacent to the leg, right? Because it's leg is on one diagonal, and then you have the whole hypotenuse, and then your adjacent hypotenuse part. That's what I'm going to call it here. So when we fill this in, x is on one diagonal as the leg, and the whole hypotenuse, that'd be from here to here. The whole hypotenuse is 5 plus 4, which is 9. So 9 goes up here. And then the part of the hypotenuse adjacent to the leg is this 4 right here. So we put 4 on this axis. I cross multiply. I get x squared equals 36. So x must be 6. Now let's take a look at the y. My y here is in fact the altitude, right? And my altitude is the geometric mean of the two pieces of the hypotenuse, hip part and hypotenuse part. So when I fill this in, I put the y on the diagonal and the two pieces of the hypotenuse, the 5 and the 4 on the other diagonal, 5 and 4. So we cross multiply. I get y squared equals 20. So I take the square root. So we get y equals, well, 20 is the same thing as 4 times 5, so that becomes 2 square root 5. Okay, moving right along. Here, the x plus 3, this guy is a leg. And because he's a leg, we're going to use this idea right here, okay? This is our second big idea. We're going to use this idea from the previous page of notes to help me solve it. So when I set it up, I'm going to put my leg on the diagonal. That's x plus 3. X plus 3. I'm going to put my whole hypotenuse, which they're telling me is 12, and I can tell it's the whole hypotenuse because they're not centering it on the part. They're trying to center it on the whole. 12. And then the part of the hypotenuse adjacent to the leg, which is that x, on the other diagonal. And we're going to cross multiply. So I get 12x equals x plus 3 times x plus 3. And now, guys, when I get something like this, I need to FOIL this. So this is a big Algebra 1 review, okay? We're going to FOIL that, so I get x squared plus 3x plus 3x plus 9 still equals 12x. Combine my like terms, x squared plus 6x plus 9 still equals 12x. I'm going to subtract my 12x over because this is quadratic. I need to have everything equal to 0. So it becomes x squared minus 6x plus 9. I need two numbers that multiply to positive 9 and add to negative 6. I like negative 3 and negative 3, so I use that to split the middle term. X squared minus 3x plus 9. Group your terms, good old AC factoring. I'm going to take an x out, so I get x minus 3. I'm going to take a negative 3 out, so I again get x minus 3. I like that because those terms match. I get x minus 3 times x minus 3. All this is still equal to 0. Well, when I set each of these equal to 0, x minus 3 equals 0, I'm going to get x equals 3. And that is my solution. All right, guys, take a minute, copy that down. I'm about to erase all this so I can do the next problem. Okay, I write big on with this type of pen, so sorry, friends. Okay, so let's look at this next piece here. This guy, now I've got an x plus 5. He's an altitude. So because he's an altitude, I'm going to use my altitude formula to solve, where I put the altitude on one diagonal, which is x plus 5, and x plus 5, and I'm going to put the pieces of the hypotenuse on the other diagonal, 20 and x. The altitude is the geometric mean of the pieces of the hypotenuse. So we cross multiply, so I get x plus 5 times x plus 5 equals 20x. I'm going to FOIL, and which gets me x squared plus 5x plus 5x plus 25 equals 20x. Combine like terms, plus 10x plus 25 equals 20x. Subtract over x squared, now minus 10x plus 25 equals 0. I need two numbers that multiply to positive 25 and add to negative 10. That's negative 5 and negative 5. So x squared minus 5x plus 25 equals 0. Group your first two terms and your last two terms. So I take out an x here to get x minus 5. Take out a minus 5 here to get x minus 5 again. This is really similar to the last problem, popping up here. So this becomes x minus 5 times x minus 5 equals 0. So when I set, they're the same terms, when I set it equal to 0, I get that x equals 5. And that's my answer. All right, guys, let's take a look at this one. I want you to take a minute and figure out which rule do you use to solve this. Take a minute and think about it. Which rule are you going to use? All right, I think we're going to use the leg rule because this guy is a leg. So we're going to set it up like a leg problem. The leg is the geometric mean of the whole hypotenuse. So I know I've got 12 on one side. The whole hypotenuse, this time we have to do a little bit of math. We know that this piece is 18, this piece is x. So the whole hypotenuse is x plus 18. Yes, you're allowed to do that. X plus 18 is the whole hypotenuse. And the part of the hypotenuse adjacent to the leg, that's that x. And we're going to do just like we've been doing before. We're going to cross multiply. X times x plus 18 is equal to 144. We're going to FOIL that or distribute that. X squared plus 18x equals 144. Because this is quadratic, I'm going to drag the 144 over. X squared plus 18x minus 144. Okay, guys, I want you to take a minute right now. Try to factor it on your own. I'll give you a second. These numbers were a bit clunkier, so you may have had to make your table of factors. When I made my table of factors, I liked the 6 and the 24. And then I used those terms to split my middle term. I took out common factors. I end up with the factored form of x minus 6 times x plus 24 equals to 0. I set both of those factors equal to 0. So I get x equals 6 or negative 24. Now, this is a geometry class. We're dealing with a real figure, a real shape. If I let x be a negative, I would have a negative length, and that makes no sense. So we toss that out. So our answer is just x equals 6. All right, guys, thank you very much for watching the video. Have fun on the MML.